Hello, welcome back to physics. We're going to be covering the concept of instantaneous velocity in this lesson. So what we're going to do is we're going to briefly review the concept of average velocity, and then we're going to talk about what it means to understand the velocity of an object instantaneously. And also in this lesson, because of the way it's all structured, you're actually going to learn a little bit of calculus in this lesson. So if you've already taken calculus, then a lot of this stuff will seem familiar, but I do encourage you to go through it because we'll be using these concepts throughout the rest of physics. And if you've never heard of the word calculus, or if the word calculus really scares you, don't worry about it. I've taught this to my kindergartner. It really isn't a big deal. I'll explain the concepts as we go, and you will understand conceptually what the foundation of calculus really is about, because the invention of calculus was done to explain nature. So we're going to be talking about the way things move as a motivation for kind of the way calculus was really formulated to begin with. So forget about calculus for now. Let's go back to the concept of average velocity. So I'm going to ask you to recall the concept of average velocity. We've done this before. It should be crystal clear what velocity means. It's meters per second or kilometers per second. So it's distance divided by time. And the way we did that before, we can write it as VAV. The AV means it's an average quantity. Some books you might see a bar over the top, meaning it's an average quantity. Some books you might even see little brackets, whatever. But we're just telling you that this is an average quantity, right? And we talked about in the last couple of sections that basically it was the final position that you ended up with minus your initial position. This is how far you move, okay? Divided by the final time minus the initial time. So in other words, you have a stopwatch, you have a final time and an initial time, that's how long it takes. And you have a final distance and an initial distance, so you subtract them, that's how far you move. And the way we wrote that down in shorthand is we said it was delta x divided by delta t. When you see these triangles, in your mind, you need to replace the triangle with the word change. So the way this Greek delta means, it basically means the change in x, however far you move, divided by the change in the time it took for that motion. You divide them, you get meters per second. See, meters per second, that is what we call an average velocity. Now the reason we called it an average velocity is because this subtraction was just over the final position and the initial position. In other words, I can go from point A to point B lots of different ways. I can go very constant, where I'm not really changing my speed at all. But I have an initial point and a final point between them, and I'll divide the distance divided by time, get average velocity. Or I can go really fast and then slow down, and I can have that still is just initial and final position in time. Or I can start out really, really slow and then accelerate like this. And so you see what I'm saying? You can go from A to B many, many different ways. And because you're only dividing how far you go over the whole interval, divided by how long it took, it's just an average quantity. It doesn't tell you anything about how you actually go between A and B. It just tells you how far you went and how long it took. So on average, that's your speed, meters per second on average. It doesn't tell you what happened in between there. But now we want to kind of get a little more detail about looking in and zooming in at what happens at any particular given time. That's why we're going toward the concept of instantaneous velocity. What is my velocity right now? Not average, what is it right now? And then 2 seconds later, what is my velocity right now? At that point, 2 seconds in the future. That's what we want to do. So to motivate this, we're going to draw a very simple motion graph right here. The simplest motion that we can probably think of. We're going to graph it. But we're only moving in one dimension, you see. We're only moving backwards and forwards. We're not moving all over the place. We'll do that later. So for now, we're just going to plot the time in seconds. That's what we're always using. And then we're going to plot its position x in meters. So you see meters per second, x over t. So we're just plotting how far you move away from some point. This is your displacement here. And how long it takes, basically. So let's go ahead and draw this guy. Let's say that my motion looks like, when I would plot it, like a straight line, like this. This is this. There may be a slight curve to that. I apologize. It's supposed to be a very straight line, okay? So what I mean by that is, let's put some tick marks here just to have things in place. 1, 2, 3, 4, 5. It doesn't really matter. I'm not going to do any calculations really with this. We're just going to be talking mostly. The numbers are important, but right now the concepts are more important. So what does a graph like that mean? That means that if I start at the origin here, at my front doorstep, let's say, and I'm walking out to get to the mailbox, straight out to my mailbox, right? So what it means is as time goes on, this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. As time goes on, I'm walking away from my house. This is 1 meter, 2 meter, 3 meters, so on. So you have 1, 2, 3, and so on. 1, 2, and 3, and so on. Time and distance, all right? And because this line is straight, there's no curving, and not supposed to be anyway in this line, that means that for every second in time that moves on, I go the exact same distance up. So I go in distance. So as I move 1 second, I go this far in distance. I go another second, I go the same distance from that point. Another second, I go the same distance again and again and again. As time goes on, I'm walking exactly the same speed. So what that means is, as time goes on, I'm moving again so many meters. I'm moving again the next second, so many meters. Nothing is changing. It looks like this might be changing because it's a slanted line, so you might think something's changing. But really what it means is I'm walking at a constant velocity. I am walking, I am making progress in distance as time goes on, but nothing is changing because every second that moves on, I move another equivalent distance. That's the same as all the other previous segments here, okay? We'll see later that if this curve starts changing or looking weird, that's when you're speeding up and slowing down. But here, when it's a straight line on a position velocity, on the position time graph, that is a constant velocity. So if we were to calculate this velocity, let's just say, like in this interval somewhere over here, how would we do it? Well, you know that average velocity is distance divided by time, delta x divided by delta t. All right, so let's just say I want to calculate the average velocity somewhere in this region. So let me pull up my handy dandy marker here. And let me say that I want to look in this region right here. Let's say from this region right here. So I'll go up at this point, and that corresponds to a value of distance somewhere between 1 and 2. So at the 3 second mark, I've moved, maybe it's hard for you to see, but somewhere between 1 and 2 meters, about 1.5 meters. And then sometime later, it doesn't even matter for this discussion, but let's say it's like 5 seconds later. 1, 2, 3, 4, 5. Here's 5 seconds. Let me mark this 5 second mark a little bit more precisely. Then I would, at the 5 second mark, I go and read off the graph exactly what is this time right here, like this. So at the time I start looking at my clock, I'm at this distance away from the house. And then at some time interval later, this is, let's call this 4, 5, 6, 7, 8. This is the 8 second mark. I'm up here, and this is around 4 meters away from the door. So if I wanted to calculate what is my average velocity from this time, I'm just illustrating it in a different way, but it's the exact same calculation as we've done before. What is this value here? We call it delta t, right? What does delta t equal? Well, this is 3, so 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. This is a 5 second delta t, right? Why? Because 8 minus 3 is 5, all right? And then in that interval of time, how far did I move in distance? You got to turn your head sideways, and the numbers are kind of a little bit messed up here, but you can kind of look here and say, well, this is 1.5, and so 4 minus 1.5, this will be 1, 2.5. So this is about delta x is around 2.5 meters. So it doesn't, because nothing is changing here, it doesn't really matter how wide or narrow my interval is, but let's just say I wanted to find the average velocity between this amount of time, right? So in this amount of time, I went 5 seconds in time, and that corresponds to about 2.5 meters of distance traveled. So how do you do it? You say, well, the average velocity is going to be equal to delta x divided by delta t. The delta x, which is how far I traveled, is 2.5 meters. And then you have 5 seconds. So you can go in your calculator and divide it. I'm not even going to write the number down because it doesn't matter. But the point is that's meters per second. Why? Because I have meters on the top and I have seconds on the bottom. So that's going to be a number less than 1, right? That's a fraction. But it still means, this unit means that on average during that interval, I was traveling that many meters every second. But the most important thing I want to illustrate to you is, what does this graphically really mean here? What it means is, what we did is we calculated, if you remember back from algebra, in algebra, whether you took it with me or you take it with somebody else, eventually you talk about graphing lines in algebra. And what is the most important thing you learn about a line? What's the most important number that governs what a line really looks like? It's the slope of the line, right? The slope, how steep it is. A line with a really steep slope has a high slope. A line with a medium slope is a lower value. A line that's almost flat has a very low slope, and a line that's totally flat actually has a slope of 0 because it's not tilted up at all. So the steepness of the line basically is what the slope is. The higher the number, the higher the slope of the line. So that's when algebra and stuff comes back into play here, because this is essentially what we have. We have a straight line position graph. So when we calculate this distance, the delta x, this is the rise. Remember rise over run? That's from algebra, right? So let me extend this to kind of show you over here. What we really did, I'm going to draw it over to the side so that you don't have to clutter up what we have here. What we did is we calculated how far up did we go compared to how far over did we go. This was called the rise, and this was called the run. So the most important thing I want you to pull out of this is this average velocity is how far the graph went up in delta x divided by how far it went over. So what you really calculated is that the average velocity was really the rise of this position graph over the run of this position time graph, because the rise was really delta x and the run was delta t. All right? So what's going on here is, because nothing is changing, because this is a straight line, what is the slope of this line here, the rise over run? Well, whatever value it is, just remember it in your head. What is the slope of the line here? 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 The slope of this line is the same everywhere. It doesn't change. And that's why, because it was a straight line, it doesn't really matter if we calculate the average velocity here. It's going to be the same exact value as if we had calculated the average velocity there. If I looked at the time between these 2 points and then looked at the corresponding distances over here, I would have different numbers for the distance and different number for the time. But because it's a straight line, rise over run, slope would be the same. So you can calculate the slope of a line between any points. It never changes. The slope of the line is always the same. Now, one thing I want to point out to you, I'll remind you later, this is what we call a positive slope. This would be a positive number because everything rise was positive and run was positive. But if you remember back from algebra, you can have negative slopes for lines. So if this is a positive slope, then this going the other direction, any kind of line going the other way would be what we call a negative slope. So I'm kind of getting a little ahead of myself, but basically what I'm saying is when you plot position time graphs in one-dimensional motion like this, the slope of this curve here, well, it's not a curve, it's a line, the slope of this line is what we call the velocity, the average velocity. And positive slopes mean positive velocity. It's positive velocity because you're going in the positive x direction as time goes on. But if the slope were backwards the other way, like if I drew it the other way, then it would mean that your velocity would be negative because the slope would be negative. And if the line actually did go down, it means that you would be going from farther away closer to your house as time goes on. So punchline takeaway, I'm going to repeat myself several times throughout the lesson. Position time curves are position time lines. When you take the slope of them, they give you the velocity. We call it the average velocity in this case because we're looking over some period of time. But the slope never changes, so the average velocity on this line is always the same. Positive slopes mean positive velocity. Positive velocity just means I'm going in positive x direction, okay? But of course I can turn around, I can go the other way, and if that happens, if I were to plot that, I would have a line that would be going the other way. That would be a negative slope, which means I would have a negative velocity. So negative velocity just means I'm walking back toward the negative x direction, like back toward the source or toward the origin. Positive velocity, going the positive x direction. Negative velocity, just going the other way. That's all it means. All right? Now, what we want to do is move along. This is what we calculate. The average velocity anywhere in this line is always the same. Because this was very simple motion. It was a straight line. What is going to happen if we introduce more complicated motion? What if your motion, if you plot it, is not a straight line? What if it's a curved line? Let me show you what that means, and that is really the genesis of instantaneous velocity. It's also the genesis of how calculus was invented, so we're going to learn a little bit about that in the process here. So what we have is a graph like this. Everything is the same, more or less, because you have time in seconds, and you have distance in meters. So everything's the same, really, as far as the plot here. But instead of a straight line, what if your position curve looks something more like this? What if you came out the door and you did something like this? Now, without doing any math, without doing any discussions, without talking about the scary word called calculus, What do you think is happening in this graph? Well, when I come out of the gate, I'll put some tick marks here if it helps you. We'll put a few tick marks just to kind of help you kind of gauge time. That's time. Here's distance traveled. What do you think is happening here? Well, I walk out the door, and 1 second later, I've only gone a very small distance. But then the next second, I've gone a little bit farther. And then as the seconds go on, it looks as if each second, I'm actually traveling a farther distance. So when I look at the very first second, I only went, according to this graph, even less than 1 meter. But then when I start looking at the tick marks way out here, see, these are just 1 second tick marks. So if I look at like this tick mark and look up here, it looks like I traveled much, much farther during this second over here compared to how far did I travel during this second. So when you have a curved position time, it doesn't have to go up like this. It could be any shape. Anytime it's changing and not a straight line, all it means is your velocity is changing. When you think about it, look at this curve. What this means is this is the position. This is a graph of position, right, as time goes on. But you can infer the velocity from it because you can see that I'm not moving very far in the beginning of my motion. But as time goes on, I start moving a farther distance for every second. And when I get way out here, I'm moving really, really far for every second. So the only way that I can be moving farther every second as time goes on is if I'm speeding up. If this is my motion, then I'm basically slowly coming out and then I'm going faster and faster and faster because toward the end I'm covering more distance every second. Okay? So what we want to do is, it was easy to calculate a velocity for this line because the velocity, the average velocity, is the same everywhere. So we could say, what is the velocity here? What is the velocity here? What is the velocity here? It's the same slope everywhere. But what would be the velocity, let's say, here on this curve? Let's just put some labels down. Let's say, what would be the velocity at point, let's call it A. What would be the velocity there? Well, it's tricky because the thing is tilted. I mean, it's curved, right? What is the velocity, let's say, over here at B? What would be the velocity there? Well, again, it's tricky because it's not a straight line. Everything's curved. How do I handle that? Well, we haven't learned it yet, right? How do we go over here to, let's look at point C, right? What's going to happen there? What's the velocity there? So now we're not talking about average velocities anymore. I want to know what is the velocity at a certain time. In other words, this is t is equal to 1, 2, 3, 4 seconds. T is equal to 4 seconds. What is my velocity right then? How many meters per second am I going right then? And then I look at this point in time right here. This is, I don't even know, 1, 2, 3, 4, 5, 6, 7, 8. That's 9 seconds. So several seconds later, 9 seconds. What is my velocity right then, at that moment? Not over some distance in time, but like right then, instantaneously. What's my velocity? I don't know what it is, but I know it's got to be faster than this because I'm covering more distance, right? And then I look here. This is like, I don't know, 15 seconds or something. What is my velocity at that point in time, instantaneously? What does my speedometer say I'm doing? I don't know what it is. I haven't taught you how to do it, but you know there's got to be a higher velocity here than here. And you know this has to be a higher, much, much higher velocity than here. Why do you know that? Because you're covering more distance every single second way up there than you are down here. So let me give you a punchline to this. What I'm going to do is I'm going to illustrate the punchline here with this simple graph, and then we're going to go draw a few more graphs to kind of mathematically define everything a little bit more. What you do, if you want to figure out what the velocity here at point A is, what's the best way to do this? I'll use this one. Is what you do is you go draw a line. Because remember we said over here, the line is the distance over time graph, and that's going to be what we call the average velocity between 2 points, right? But we said the slope of a line is what the velocity is distance over time. But everything is changing here, so I can't really, easily calculate what's going on. But if I could draw a line that just touched this curve at point A, just there, only one spot. So you got to imagine what we call a tangent line. It's a line that only touches this blue curve at one spot, and it only touches it exactly as that tiny little dot called A. And that's what we call tangent. It isn't intersecting the curve like this. It is literally just kissing it right there at one spot there. If I could draw that line there, and if I then could calculate the slope of that tangent line, which is, we know how to calculate slopes of lines. We've been doing that all day. We've been doing that in algebra. Then the slope of this line that's tangent to A, we could then say that's basically the velocity at A, right? And then how would we handle B? Well, if I got a ruler out, and I drew a line that just kissed that graph, it looks like it's kind of intersect. It's because my marker is thick. You have to imagine a line that barely, I have to draw it almost very thin, that barely just touches at one spot. Do you see how the slope of this tangent line is less than the slope of this tangent line, which is the slope of less than the slope of this one? In other words, the highest slope line is this one. The medium slope line is this one, and the smallest slope line is this one. That means that at point C, whatever it is, this will have the highest velocity, right? I can't even spell highest. Highest. The highest velocity. And this one I'll call, this is a higher velocity. And I'll call this one a low velocity, lower. I'm just comparing them. We're not putting numbers to anything. This is the lowest or the lower one. This will be a medium velocity or slightly higher than this one, and this will be the highest. Why? Because the slope of the line that just kisses each of these curves at that one point is increasing as time goes on. So I have a lot of notes here. I don't want to write them all down. I want to verbally tell you, so let me just make sure I did this. Slope of the curve is different everywhere. The slope of this curve we go on in time. We talked about that. Slope at a point is the slope of the line tangent to the curve. Talked about that. And I already mentioned this verbally, but if you have a positive slope line, it looks something like this. It's angled something like this. And what that means is this is a positive velocity if it's angled like that with a positive slope. Now, I haven't drawn it in this curve, but you can also have negative slope line. And that means that the tangent line would look something like this. And that means that the velocity would be negative there. Because of course you can have positive and negative velocities, and it's all going to be reflected in whatever your position time graph looks like. Positive velocity moves to the right or in the plus x direction, negative velocity moves toward the left or the negative x direction. So positive velocity is moving toward positive x, negative velocity is moving toward negative x. All right, so this was qualitative is what we call it. Basically, I want to explain to you the big picture so that we can get down and dirty and actually figure it all out. How do we actually calculate the slope of this line tangent to A? Well, let me go through and walk through how it's done. It's still going to more or less be a math lesson, but it basically teaches you how you do it, and you also learn the basic concepts of calculus at the same time. So let's estimate. We're not going to calculate the slope of this line right exactly here because I don't know what this line exactly is, and I don't know exactly how to calculate the slope. But instead of actually finding the exact instantaneous velocity, let me get an estimate. Let me estimate this velocity at A as best as I can. Estimate the velocity at point, I can't even spell, point A, right? So what I want to do is draw several graphs here. The first one's going to look, how big do I want to draw these? Yeah, I think I want to draw them. Yeah, I think I want to draw them a little bigger, like this. We're going to do 3 of these things. This is the time in seconds, and this is the distance in meters. Okay? So what we're going to do is we're going to do a little bit of graphing, but it's not going to take very long at all, I promise you. So what we have is our original curve, something like this. And all I know is that here is my point A. I want to figure out what is the velocity there. So I got to figure out what is the slope of this curve at A. I don't have any idea what it is, but what I'm going to do is I'm going to estimate it by finding a far away point called point B. Now what I'm going to do is I'm going to, whatever A and B are, it doesn't even matter what they are. What I'm going to do is connect a line segment, I'm going to try to draw that straight, between A and B. That's just a line segment. And I'm going to say that whatever the slope of this line segment is, it's got to be sort of kind of close to whatever the slope at A is. But it's not obviously very exact because B is very far away, but I can still use it as a very rough estimate, right? So then what I'm going to do is say, how am I going to calculate that? Well, I have a line here, and then we'll do something like some tick marks like this. And I could say, here's doot, 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 something like this. So I have something like this. So what I have is between these 2 points here, I have some delta t. So this is how many seconds have elapsed between A and B. All right. And then I'm going to go over here. We'll say, we'll just put some tick marks here. Something like this. And so we have a corresponding, let me switch colors for that one. We have a corresponding, at this initial point, we have this spot here, and then at this final point right here, we have some final point here. So as time goes on, whatever it is between A and B, like this could just be literally a point on the graph, and this is another point on the graph, how far in time has elapsed, and then for those points, how far did I travel? And then I could say, well, the distance between here, we call it delta x. This is exactly the same as what we did to begin with. No difference. I could put numbers on the graph if you want, but it doesn't matter because all I'm doing is I'm saying I'm picking an initial time, picking a final time. That's what I call delta t. Corresponding to this, I have some initial position, final position. That's what I'm calling delta x. And I do the calculation. Here, I'm saying I want to find the slope here, but I have no idea how to do that. So I'm just going to pick some point far away. I'm going to draw a line segment to it, and I'm going to say that this line, whatever it is, has some slope associated with this line segment. Okay? So what this is going to mean, this slope is going to be the average velocity between A and B. Of course it's the average velocity because what's going on is so many seconds elapse, so much distance is traveled. As I said before, average velocity doesn't tell you anything about what's happening inside the interval. You don't know anything about that. You're just looking at the endpoints. So I'm looking at the endpoints. I have a curving position curve here, but that's okay. This is just a rough guess. So I'm going to calculate the slope of this pink line right here. How do I do it? Well, I do it the same way I do all of these things. I basically say the velocity at point A is approximately equal to, as a really, really rough approximation, I'll call it average velocity, delta x, delta t. So let's say, 6 meters of distance and like 7 seconds of time. You divide them, that's an average velocity. That's the slope of the pink line. It's not really close, but at least it's kind of sort of close. But let me ask you this. If this is not so great of an approximation, how can I make it better? What would I do to get a better estimate? I don't know how to get the actual answer of the tangent line there, but how can I get a little bit better? Well, I could take this point B, and instead of looking at a point far away, let me move it down closer. Just not even really, really close, just like an intermediate distance, like somewhere around here. And let's see what happens if I were to do that and redo the calculation again. So what's going to happen is I'm going to draw a little thing here, and we will do this exact thing again. Right? So here we have t in seconds, and we have x right here. We have the exact same, well, trying to draw the exact same. It's not exactly the same, but that's the position time guy here. And then what we're going to do is we have somewhere around here is pretty close to point A. And instead of being really far away, I'm going to bring it in somewhere right around here. We'll call that point B. Now what's going to happen here? Well, I'm going to calculate the slope of the line connecting these 2 points. Something like that. I know it looks like I'm tracing the curve. I'm not really trying to. It's a line segment. It's not going to be right on top of the blue line because the blue line's curved. But still, it's a line segment, and I can still find the slope of this line between A and B, and what will I get? I will get the average velocity between A and B because there's going to be some tick marks here, like this, but here in time, there will be some delta t. So many seconds elapsed. And then corresponding to these points, there will be some delta x, right? So what's going to happen is, I would say the average velocity, what is going to equal? It's always the same thing. It's going to be delta x divided by delta t. Now, of course, the delta t that I'm choosing here is much, much smaller. If I put the tick marks in place compared to this, you'll see instead of maybe 6 or 7 seconds, maybe this is like 3 seconds. And then correspondingly, the delta x will be a shorter distance because I'm looking at a narrower window of time. But when I calculate delta x over delta t, I'm calculating the average velocity between A and B, which is the slope of this purple line. So the slope, I keep using the word slope, because the slope of that purple line is what we're calling the average velocity between A and B, delta x over delta t. So that's better, right? Because when we look up here, the slope of this line was pretty far away from what we kind of think the tangent line is here. But as we move B in, it's physically closer, so it's getting physically closer, so it's still not a great approximation, but it's much, much, much closer, right? So as we move B closer, we're getting better and better. How do we get B as good as we can? Well, what we do is we get it as close as we can. So we draw this, we say this is T, we say this is X in meters, as always, and then I'm going to try to do my very, very best with this drawing because it's the most important one. So here we have something like this, okay? And then over here, we have point A. We want to find the instantaneous velocity at point A. Now, initially we had a point B here, and then we brought it in closer as a better estimate. Well, if we bring B here, it's a little bit better. If we bring it closer, it's a little bit better. If we bring it in closer, it's a little bit better. So what I'll do is I'll bring B really, really, really close. Physically, I would bring them as close as possible, but to draw it, I have to, I have to do something. I have to put it physically separated so you can see it. But what happens is here, between A and B, I can have some incredibly tiny delta T, and then corresponding to this, I can have some incredibly tiny delta X. And I can't even draw it, but between A and B, there would be a tiny, tiny, tiny line segment. And as you bring these things really, really close together, that line segment's going to get really, 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 really small. But it's going to get closer and closer and closer to the tangent line at A. But before we get there, what do we say here? We say that the average velocity between A and B, what is it? We just say it's delta x divided by delta t. Same exact thing. It's just that delta x is really, really small and delta t is really, really small. But still, I can divide two small numbers, no problem, and I'll get a very, very close approximation for the slope of this tiny line segment there. All right? Now, here's where the magic happens. What we want to do is find the exact instantaneous velocity at point A. So we don't know exactly how to do that, so we pick a faraway point, find the slope of the line segment between them. Okay, that's a good approximation. We bring it closer, we find the slope of that next line segment. Okay, that's pretty close. Now we bring it really, really, really close. Then we get so close, we can say that the actual instantaneous velocity, the slope of the line tangent to the curve at point A, is going to be the following thing. What we say is that it's delta x over delta t. All of that is the same. But what we do is we take what we call the limit. As delta t approaches 0, that's what the arrow means. It means it approaches 0. And we're going to say that v is equal to, so we're not putting average here. We're not saying average velocity anymore. We're saying the actual instantaneous velocity at point A. Taking this process in the limit, if we shrink delta t tiny, tiny, tiny as it approaches 0, of course, it can't, you're not really going to let it get to 0, right? Because if you let it get to 0, then you're dividing by 0, right? But what you do is you let it get really, really small. Like maybe you start off looking at 5-second difference, then a 3-second difference, then a 2-second difference, calculate the velocity, then a 1-second difference, then a half-a-second difference. As you get smaller and smaller in time, you're getting a better and better estimate for the velocity at point A, right? Let's take a half-a-second. Let's take 0.25 seconds. Let's take 0.1 second. Let's take 0.00001 second. Let's take 0.000000000000000000001 seconds. We don't let it get to 0. This means it approaches 0, but it never gets to 0. Because if you get to 0, you're going to run into problems dividing. But if you let it get really, really tiny, we say that we take the limit. What happens to this fraction as we take that limit? That is called the velocity, the instantaneous velocity at a point. This is the slope of the line tangent to curve at point A. Whoops, can't even write A. Point A. So if we start all over, well, actually, I'm going to start over. I have it right here. What we want to do, we said initially qualitatively, I said, I want to know the velocity at point A. Well, let me put a line there, put it just kissing the curve, just touching in one spot. The slope of this line at A is going to be the velocity, the instantaneous velocity at A. And now I'm telling you the way you do it is you you kind of do a little bit of magic here, really. Well, what you actually do is you find a tiny, tiny line segment between two tiny points on that curve, so close together that you need a microscope to see them, right? But still, they're going to be separated in time and then separated in distance. You divide those two things, and once you bring that very, very close in, then you calculate what we call to be the instantaneous velocity at point A, all right? What you just learned here, that the velocity is the limit as this time goes to 0 of the division of these two things, a slope of a line, basically. This is about half of Calculus 1. So all that happens when you go through Calculus 1 is you learn all of this stuff, and then you learn about how to actually crank through the math and do all of this stuff for lots and lots and lots of different kinds of problems. In physics, all I want you to know is that when you plot a position-time curve, the velocity at a point is basically going to be equal to the limiting process of the slope of the line between 2 points on the curve. All right? And it's mostly just for you to understand that's what instantaneous velocity is, and that's how it compares to average velocity. We'll have some problems that actually use this definition, but not really, honestly. It's mostly a conceptual thing for you to understand that the curve can be going everywhere, position curve. The slope of the line tangent to that curve is what we call the limit of this guy, and that is going to be what we call the instantaneous velocity at that moment in time. How fast are you going?